One of the main purposes we'll have for using differential equations is using differential equations to develop models of various physical situations. You've probably done this before in other contexts and not come up with a differential equation for your model. The only thing that makes using differential equations different from other model building situations is that there's some sort of rate of change involved. And a rate of change is going to, of course, become a derivative, and that derivative is what will make your model a differential equation. So let's look at some examples. One example is Newton's law of cooling. Now, Newton's law of cooling says that if you have an object sitting in some ambient environment, then the rate of change of the temperature of the object is proportional to the difference of that temperature from the ambient temperature. And the ambient temperature is assumed to be constant in this situation. You can see that we have a rate of change, the rate of change of the temperature of the object. And so it makes sense that when we describe this mathematically, we'll get a derivative showing up. So let's build a model of this situation. Now the thing we're trying to describe is, or the thing that the law of cooling describes, is the temperature of the object. So let's name that capital T. And since it's warming up or cooling down, the temperature will be changing. So the temperature is actually a function of time. So let's write it like this. Capital T of little t, this will be the temperature of the object at time T. Okay, and there's another temperature in this situation, and that's the ambient temperature, which we're assuming is constant. So let's say that the ambient temperature is, let's call that T sub m. Okay, so another key word in this situation is right here, proportional. So that's just a term of art that tells you that one thing is a constant multiple of another thing. So when we say that the rate of change of temperature is proportional to this difference, that means it's a constant multiple of the difference of temperatures. So with all of this in mind, we can just write down an equation that basically translates this entire thing, Newton's law of cooling, into an equation. So let's see, the rate of change of temperature, well, that's going to be d capital T d little t. Okay, so that's proportional to, so is equals. Proportional to, that means it's a constant times, so some constant times. And so I'm using k for our constant. Since we don't know what it is, we have to use a new symbol for it. We don't know what it is, but it is constant. So rate of change is proportional to, so a constant times the difference in temperatures. So difference between the temperature of the object and the ambient temperature. Okay, so here's a differential equation that describes Newton's law of cooling. We should think about what are the possible values for all of the constants in this model. So for k, for example, well, as far as we know initially, k could be any real number. But not all real numbers makes physical sense in this situation. So imagine that this difference in parentheses is positive. That means that the object is warmer than the environment. And if the object is warmer than the environment, then the object should cool down. That means the rate of change should be negative. So if the stuff in parentheses is positive, the result should be negative. That means k should be negative. So that makes us think, well, k probably should be negative. But what if the object is cooler than the environment? That means this difference in parentheses is negative. If the object is cooler than the environment, then the object should warm up, and so this rate of change should be positive. So if the stuff in parentheses is negative, because the object is cooler than the environment, and we're multiplying it by a negative k value, that would produce a positive derivative. So still we need a negative k value. So it turns out for this equation to make sense, to describe Newton's law of cooling, this constant of proportionality has to be negative. What about the ambient temperature. Well, I guess the ambient temperature should be far away from absolute zero, because if you're near absolute zero, weird things start happening. You can't go below absolute zero for one thing, and another thing is quantum effects start being important. So we should have ambient temperature larger than absolute zero. Okay. There's one example that produces a differential equation just because it's describing a rate of some kind. Let's look at another example. So for this example, we're going to be thinking about a mass hanging from a spring. And springs are, as long as you don't stretch them too far, springs are governed by Hooke's law. And Hooke's law says that a spring exerts a force proportional to the distance that it's stretched. Not every spring behaves in this way, but most simple springs that we're familiar with do. Since there's this magic word proportional, that means there's going to be an arbitrary constant involved in this situation. So let's translate Hooke's law into an equation. So the force that you get is proportional to, so it's a constant, times the distance that it's stretched. And we can use x for the distance that it's stretched. Something that isn't obvious about this equation is that it actually matters which way you stretch the spring. If you stretch the spring, then the spring pulls, and if you compress the spring, so that would mean that this displacement is negative, if you compress the spring, then the spring pushes. So always the force should be in the direction opposite of the displacement. And that means either k should be negative or you should have a minus sign out front, one of the two. If we're putting a minus sign out front, then k should be positive. Okay, well this isn't a differential equation yet. Let's see if we can put this into a larger context that does produce a differential equation. So the situation that we're describing here is we have a mass attached to a spring whose neutral position is at x equals 0. So we have a spring like this, and then there's some mass. And it's at x equals 0, that's the neutral position of the spring, so we can imagine giving this a stretch and then letting go and seeing what happens. Once we've let go of the mass, the only horizontal force that this mass experiences is the spring. So we should be able to use, say, Newton's second law to figure out how the force on this mass gets turned into motion in this mass. So Newton's second law that's the one that says force equals ma. And in this context, right, acceleration is the second derivative of position, and in this context, it's the x coordinate back and forth that tells us our position. So we need the second derivative, that is the second time derivative, of x for acceleration. Now the only horizontal force that this mass experiences is coming from the spring. So that's this spring force up here. And so the force should be minus kx. Okay. So this gives us a differential equation for this mass on a spring. Now, and remember, k has to be positive, and as far as we know, mass also always has to be positive. Okay, now this description of the situation does do some simplifying. In particular, it ignores any friction that might be in this situation. If you want to add other effects like friction, you need to make your differential equation a little more complicated.